So this video is going to be working some problems on the uniform acceleration problem set 1. I will work 2 problems to show you how to use the graphs to solve these. So the first thing that you need to do is sketch the graph. We're just doing a sketch, and then show all your work and label with units and use sig figs in your answers. So we want to look at problem number 2 here, and we're going to have a car that starts from rest and accelerates for 5.2 seconds, and then we will try to label these values on the graph so that we can use them to solve the problem graphically. So if it starts at rest, it's starting here, and at uniform acceleration means that slope is constant. And I'm going to say this is moving to the right just to simplify and not have to work with negative values. And there's my constant acceleration. And it tells us that it does this for 5.21 seconds. And so that would be labeled here. Now, this distance that it moves is 110 meters. That distance is the displacement without a sign on it. So that is this area under here. So we have the area of this triangle is this area underneath there. Now, we want to figure out the acceleration. Well, acceleration is the slope here, value, or we have acceleration right here, the value. Okay? So we need to figure out what is the acceleration here. Now, since we have 2 pieces of information given to us in this graph, we're going to be able to solve something there. So we know the area of a triangle equals 1/2 base times height. So if I fill in, the area is 110 meters equals 1/2. The base on this triangle is time. The height on this triangle from here to here, that is really the change in v. So it looks like I have 110 meters equals 1/2 5.21 seconds times the change in v. Take 1/2 of 5.21. I got, the answer was 42.23. I'll just go 2 meters because it's really got 2 sig figs in the problem here, and we're just going to carry it one part. Meters per second. That's the change in v. Okay? Now, the change in v is also the area underneath here. So we just figured out the value for this. So this equals 42.2 meters per second. And isn't the area of this, that area, it's a rectangle, isn't it? Base times height. So now we have this area equals the base times the height under here, and that equals, the base is time, so it's 5.21 seconds, times the height. The height would be the acceleration. So it looks like we now have 2 variables and we can solve for this. So it looks like we get 42.2 meters per second divided by 5.21 seconds. The seconds is going to be used in our answer, and if I divide that out, it looks like it's 8.1 meters per second each second. So that means I'm changing my velocity by 8.1 meters per second each second. So that would mean if I started out at rest, and that's what it says, so time is 0, at my velocity at 0 time is 0. At 1 second, I would be going 8.1 meters per second. At 2 seconds, I'd be going 16.2 meters per second. At 3 seconds, I would be going 24.3 meters per second. At 4, I would be going 32.4 meters per second. So you can see the velocity is increasing each second by 8.1. That's what that means. So these units can either be meters per second, or another way they're sometimes expressed is meters per second squared, because it's really meters per second times 1 over a second if you analyze the units. So that's example 2 done. Okay, we want to do another example on this sheet, and this one has to deal with free fall, so it's a little bit different because it's still constant or uniform acceleration. So we have Michael Jordan performing a vertical leap, and they tell you how high he can leap off, and then they want to know what his takeoff speed is. So if I did like a motion map here, at the ground, he would, once he gets off, he's going fast, then he's slowing down. He reaches the top of his leap, then he starts to speed up coming down, and then he's going fast again right before he hits the ground. And they want to know what is his initial velocity once he comes off the ground. So we're saying he's going to return back to where he started. So he's going fast. So this would be his initial, going fast, and then returning back to the ground. This right here would be at the top of the leap, the peak. That's 0, right there. Because he's not moving any more here, up or down. He's just changing direction at that point. So momentarily, it is 0. So really, if we look at this, since he's returning to the same spot, the triangle here should equal the triangle here. So you could analyze either part of this and use it. I'm going to use the second half. Okay, so if I use that, I need to see what I know. I guess there's another piece of information I know. Anytime we are falling through the air or moving through the air, we know the acceleration is constant, and it would be that negative 9.81 meters per second each second. Okay, we know that that is constant. Okay, now to look at this, he's moving 1.29 meters up, and he's also moving that 1.29 meters when he comes back down. So if we look at this 1.29 meters is that area, and since he's coming down, we're going to give it a negative sign. Okay, we could also put the 1.29 up here in this area, but I'm going to look at the second half of this. Really, those two triangles are the same since he's returning to the same spot. Okay, now we want to figure out what is his velocity initial. Well, if we can figure out this triangle, and it's identical to this triangle, same thing. Okay? Now, if we look at this, we know the area for this one right here, it's a triangle, equals 1/2 base times height. So I'm going to fill in negative 1.29 meters equals 1/2. The base of that top triangle is time. The height is the change in v. Now, we don't know the time, and we don't know the change in v. So we need to do a little substitution in here. We have two equations that we have used throughout this year that we figured out, and one was velocity average equals the change in x over the change in t, change in position over time, and the other one is that acceleration average equals the change in v over the change in t. So I have change in v here that I want to solve for, and I do have acceleration here. So I'm looking which one has acceleration in. It is this one. I can rewrite that and say acceleration times the change in t equals the change in v. I'm going to substitute this right in here for the change in v. Okay, so I'm going to rewrite this. So I got a negative 1.29 meters equals 1/2 t times a times t. Write that a little bit nicer. AT squared. So now I can plug in, because I do know the acceleration due to gravity is a negative 9.81 meters per second each second times t squared. So I need to solve for t. So I got a negative 1.29 equals meters divided by 1/2 of a negative 9.81 is a negative 4.905 meters per second each second. And I need to get rid of the square, take the square root of that. I end up getting a time of 0.5128 seconds. Now, I have to recognize that that time is only for this part of the motion, okay? And they're asking you for hang time, so we want the total time. So since they are identical, all I'm going to do is take that times 2. So my total hang time is 1.03 seconds. There's my answer for hang time. Now, the other part that they're asking you to do is figure out what is the velocity initial, okay? So we know the total time for this, or we could use, if we want to go back and just use half the time, if we want to use just that half time, we know this is 0.5128 seconds. I could figure out what my change in velocity is right here, that area underneath there, remember? The area underneath the A versus T graph is the change in velocity, and the change in velocity is always the velocity final minus the velocity initial. Okay? So this area, for this graph, it's a rectangle. So the area of base times height. So the base is time, and I'm going to just look at half of it, 0.5128 seconds, times the height, which is that negative 9.81 meters per second each second, equals my change in V. So my change in V for this example is a negative 5.03 meters per second. Okay, now this is my change in V, which now I can plug that into right here. So let me rewrite this. My change in V equals velocity final minus velocity initial. So this is 5.03 meters per second equals the velocity final. If we're looking at this, the velocity final, and we want to go initial, and remember these two triangles are identical, and I just looked at the first half because the time for that is the same as the time for this. The velocity final, when he's right here at this peak right there, that's your final. If you're looking at half of it, is 0 minus, oh, velocity initial. Doesn't this have to be 5.03 meters per second? There's our answer. That's the velocity initial that he is coming off of the ground when he makes that vertical leap. So that should be two problems that get you started with working with these on this sheet. I would recommend you do these graphically, that you sketch the graph and then use the area, the slope, and any other information to solve. You should know the area of a triangle and a rectangle. You should know those equations. That should be nothing new. And then we do have two equations that we have used throughout this. And really, this velocity average, that's just the slope of the position time graph. And acceleration average, that's just the slope of the velocity versus time graph. So those are just common things that we have been using. We can go over any problems if you have any trouble with these and check your answers.